reconstruction software, and also detector performance. That's all. Thank you.
Thank you very much for interesting talk. Although it took longer, 5 minutes longer, therefore I suggest that we shift all questions to the discussion session. Okay. Now, please stop sharing screen. Now it's my talk. Do you see my talk?
Yeah, we can see your slides.
Okay.
Yeah.
Okay.
Okay.
Okay. Let's start. I will talk about phase diagram of strongly interacting matter and how should we study it in heavy ion collisions. The outline of my talk is simple. I will try to look from the big scale about our results and problems. Then I will give a few examples of crude approximations. Then a few words will be devoted to the fate of nuclear multifragmentation community, which I hope we will avoid. Then I will briefly tell about some results about exactly solvable statistical models which are related to the physics we studied. Then very briefly I will try to show the relation between the induced surface and curvature tension concept for equation of state and its relation to morphological thermodynamics. Then I will conclude. So I will skip this diagram because everyone knows it well. So let's discuss our basic motivations. The first, we want to find the QCD phase transitions experimentally. And the second motivation is that we want to locate 3 critical endpoints experimentally. And the third one is that we want to convince our colleagues and the physics from other communities that the goals 1 and 2 are achieved. Now, if you look at the first phase diagram of the strongly interacting matter in the plane of temperature and baryonic density, taken from Khabib-Parisi famous work, you see that there is the second order phase transition curve. So it is 45 years old already, and then the question is, have we really gone far from Khabib-Parisi phase diagram? Okay, let's discuss also, I just remind about our basic tools. So the experiments on heavy ion are going almost 40 years from now, till now. Latest QCD, computational and analytic is about the same age, 40 years. If we count from the Hagedorn paper, which was pre-QCD phenomenology, then our phenomenology tools are 55 years old. Don't you think that after so long time, first, we did not find much in the experiments to reach our original goals 1 and 2? And the second thing, why we do not care about such a bad situation in my case. Okay, let's discuss some objective reasons, but I would like to spare some time and do not go into details of these 3 first one. So we know that the confinement phase transition has no well-defined order parameter in presence of quarks with realistic masses. So the second reason is we really don't know on theoretical side what is the phase transition in finite and the short-living system. And as several times at this conference it was pointed out, it is tremendously complex to model and understand the phenomena which occur in heavy ion collisions. And I would add one more fourth reason is a separate one, that in fact, another objective reason is that we face the fundamental problems which were not so far solved by other branches of physics. And let me give you this simple example of the objective reason for. There are two phase diagrams. The left one is what we are discussing, and the right one was taken from Wikipedia for usual some ordinary substance. Yeah, and you see critical endpoint on both of them. But till now, we don't know what is the physical reason that the first order phase transition curve between liquid and vapor is terminated. Experiments show that at critical or tri-critical endpoint, the surface tension coefficient sigma is 0. Below it is below critical endpoint, it is critical temperature, it is positive, but what is a value above critical temperature? So, and this is a non-trivial question, and so far the only reason which I know was that the condensation of hadron into a large bag of core-gluon plasma, and similarly to other substances, is the negative value of surface tension coefficient at supercritical temperature. Now, but there are also subjective reasons, and one of them is that we very often use crude approximations, which are not suited to model finite systems. A typical example is the mean field approximation, which is working very well for infinite system, but unfortunately, typical mean field approach cannot be used to model phase transformations in finite system, because usually it has phase transition if the system volume is very small, just contains one nucleon. Also, so far I have not seen any mean field theoretical model which contains all existing hadrons and resonances. And therefore, practical conclusion is that it is hard, or if it is even possible at all, to exactly transform particles from mean field model into real particles measured by detectors. Moreover, if you look at the critical exponents shown here for van der Waals, universality class, and those which are relevant to QCD, they're shown in rows here. So you see a large difference. So one cannot truly study the QCD critical endpoint with the mean field approximation, because it belongs usually to the universality class of classical system, like the van der Waals. And therefore, the heat capacity or the per meter exponents, they behave differently. And then we will have different predictions. Moreover, up to now, we do not know what is the finite volume analog of critical endpoint and how to define it rigorously on theoretical side. Then the question is, what is to be done? I believe that there is no other way for us. We have to make the theory of liquid-gas phase transition for finite system without referring to the thermodynamic limit during the next 2 years. Otherwise, our future will be similar to the nuclear liquid-gas phase transition related to a multifragmentation phenomenon. I will briefly show a few slides about this. The multifragmentation was predicted in 1985 by Bondorf, Mishustin, and their collaborators. Then experimentally, it was discovered 10 years later. And the whole point is that till now, they're discussing the ultimate signals of phase transitions in their reactions. I have to point out that due to the absence of strong hydroflow, the signals they are measuring are much more clean. Moreover, the quality of their data predictions with their codes is really beyond our dreams in heavy ions. However, due to a strong role of Coulomb interaction at late stage, they really have no thermodynamic limit and hence no proof of phase transition existence. And I remind you that actually the presence of a Coulomb interaction, if we're searching for critical endpoint, will be our headache soon. Now, just to illustrate the quality of their data predictions, this slide was taken from Igor Mishustin talk. On the left-hand side, you can see their prediction. Yeah, and the solid curve is the typical behavior of quantum liquid, while dashed curve is the gas of nucleons. And you see, they predicted it, and on the right-hand side, you can see how it was measured. And I would like to stress that even this little bump on the left-hand side picture was measured and supported. And so it's really nice. However, few words about their problems. So what is multifragmentation for those who are not familiar with nuclear physics? So suppose you have such a reaction, A plus B nuclei, then you measure the nuclei in the final state. And then you plot the probability to find the this large nuclei. And you can see that there is a peak, which is called compound nucleus. And this is just the droplet, large droplet of nuclear matter. And I have to say that its probability is comparable to the probability of a deuteron. So they do see liquid. But then if you excite your system, your original system, by about 3-4 MeV per nucleon, then immediately the distribution function goes to the multifragmentation regime. And so this peak disappears and you have only multifragment. And the explanation to such change is very simple, is shown on the figure below. So if you have phase diagram in a plane of temperature and baryonic density, then you have gas, mixed phase, and liquid phase on it. And if your final states belong to the mixed phase, you go to compound nucleus regime, so droplet of liquid plus vapor. But if your final state belong to the gas region, so there is no droplet, and you have only this multifragmentation regime. So explanation would be nice, but unfortunately, there is no such phase diagram in the thermodynamic limit because of Coulomb repulsion. Now, my belief is that one realistic possibility is to use the statistical mechanics or statistical models. And let me briefly show. The first statistical model is called statistical bootstrap. It idea belongs to Rolf Hagedorn, but the equation was suggested by Stephen Frauche. Then it was solved analytically by Yellen. And this is really beautiful model. I love it. And it leads to the Hagedorn or asymptotically exponential mass spectrum of heavy hadrons. And this Hagedorn mass spectrum follows from many models, including QCD, enlarging NC limit, but unfortunately, experimentally, the Hagedorn spectrum is not observed experimentally. And the reasonable explanation is that hadronic resonances or bags of mass M have large width which is proportional to square root of their mass. So they cannot be observed experimentally. The next outstanding model was Kapusta model, gas of bag, suggested in 1981, and it is based on MIT bag model. However, it has pathological defect, and due to it, it cannot have the usual critical or critical endpoint. And I will discuss it in a minute. But experiments and exactly solvable models of liquid states, they show that real gases do not consist just of molecules. They consist of droplets of molecules of all possible sizes. So they have, besides the molecules, also dimers, trimers, foamers, and so on. And actually only this fact explains the reason of how and why the liquid appears from the gas. I realized this after solving this simplified version of statistical multifragmentation model, that the key element is the temperature-dependent surface tension coefficient of large droplets, or bags, or nuclear clusters. And this element is not present in Kapusta gas of bag model. What do we know about the surface tension? I already told you, but what we do not know, it is its value at temperatures above critical endpoint temperature. But there is nice prediction, and this is why I'm talking about it, that at critical endpoint in infinite systems, the mass distribution of large droplets or bags or nuclear clusters should have a power law instead of some exponential law. By 2005, I already had an exactly solvable statistical model of surface deformations of large clusters. And as output, there was this formula in the left bottom corner that the temperature dependence of surface tension coefficient is linear in temperature, and many substances indeed showed this. However, this is the surface tension coefficient of one cluster, one big cluster. But the conclusion which I came was that at large temperatures, the surface tension must be negative. Using this idea, our group worked hard, and we worked two set of models with 3 critical endpoint and critical endpoint. So on both of them, the black curve shows the first order phase transition. Below it, sigma is positive. And the dashed red curve to the left of the 3 critical endpoint on the upper panel has second order phase transition, while to the left-hand side of 3 critical endpoint, it has a crossover. And in both of these regions, sigma is negative. Then we continued, and a few years later, we found the solution with critical endpoint. But I continue. That in the meantime, I also exactly solved a couple of statistical models for finite volumes. And since no one was interested those days in exact solutions, then in 2012, I turned to analysis of hadronic yields. And the main idea behind it was to improve the hadronic part of our exactly solvable model in order to go beyond the second virial coefficient approximation and extend model to high Pagan fractions. During 2013, 2017, our group developed new hadron resonance gas model, which with only 2 or 3 extra parameters compared to 56 of the best GSI version of hadron resonance gas model describes all the data. In my opinion, it is most successful version of hadron resonance gas model, although I have to say that our colleagues from GSI completely ignored it. And moreover, together with young group members, Dima Linichenko, Alexei Ivanitsky, and Violeta Segun, we solved several hard problems of hadron data description, which no one was able to solve during about a decade. And moreover, we, in addition, found some new signals of 2QCD phase transition. You see, the point is that high quality of the data description of hadronic multiplicity ratios allowed us to elucidate new irregularities at chemical freeze-out from the data and to formulate some new signals of 2QCD phase transitions. And it is interesting that our results are consistent with the Giesen group results published in this paper from 2016. However, the main outcome of our activity was that we derived heuristically and rigorously the hadron resonance gas model, which is based on the concept of induced surface tension. In other words, the surface tension induced by interaction of each particle with the medium. Here there is the system of these two equations. I don't want to go into great details. First equation is for pressure. Second is for the induced surface tension coefficient. Phi I is the thermal density of particle of sort I. Then RK, VK, and SK are respectively the hardcore radius, eigenvolume, and eigensurface of hadron of sort K. And here there is this new term shown in red color. So if alpha is 1, then we get just usual van der Waals approximation. But if alpha is larger than 1, in particularly equal to 1.245, then our model is able to reproduce not only the second, but third and fourth virial coefficients of the gas of classical hard spheres. The great advantage of this approach is that number of equations is always 2, and it doesn't depend on the number of hardcore radii. So this gave us a huge advantage over other hadron resonance gas models. Then I was lucky last year to invent a method to rigorously deal with the mixtures of particles which have multi-component hardcore repulsion. And then I was able to derive directly the equation of state from quantum grand canonical ensemble partition. These results were successfully generalized together with a student of mine, Nazar Yakovenko, and my colleagues, Larissa Bravina and Evgeny Zabrodin, to describe the equation of state for mixtures of hard disk, even, and hard spheres, classical, of course. But then we had to generalize our concept of induced surface tension and include into it the curvature tension term. Presently, we are working on the extension of this model to the mixtures of hadrons, nuclei, and bags. But a few months ago, I learned a bad truth, and I have to confess, I was greatly surprised by the fact that people from other communities are reading my papers. And I found that Ronald Roth and his collaborators from Stuttgart, they came to a similar conclusion about the full free energy of the fluid existing in a convex container, which has some arbitrary shape, but convex. So here there is volume, V as a surface, mean curvature, and Gaussian curvature X, and it is a very general result. And it says that the thermodynamics of fluid is completely described by this free energy. because I remember 30 years ago, there were discussions, how many invariants do you need to study the thermodynamics of a large system with arbitrary shape, but it is finite. So people thought that you need infinite number of invariants, but fortunately we need only 4 of them. Here P is pressure, sigma is mean surface tension, average over the surface, and so on. So you can look into the original papers of this group, they're given here, but now you can apply this idea to study the free energy of your large nucleus or very large quark-gluon plasma bag. So then for 0 pressure, you will get free energy, which will define you the degeneracy factor of your nucleus or bag. Yeah. So this is the so-called eigen free energy, which you can calculate through the surface tension and curvature tension and so on. But now I would like to tell you that this approach is based on the Heidegger theorem, and it is valid for interaction of finite range. But now you can apply the same approach to a convex rigid body R inside of the fluid. And so if VR, SR, and CR, and XR are respectively its eigenvolume, eigensurface, eigenperimeter, and so on, you will get slightly different expression because of the sign, because it is other topology, and it coincides with our finding, but we always found that this psi coefficient is 0. Actually, now combining these 2 free energy, internal and external one can naturally explain the reason why the surface and curvature and other tensions must vanish at the critical endpoint. So the second conclusion is that our group was on the right track. Fortunately, in addition, our derivations are valid for mixtures of rigid bodies and also for quantum statistics. And generalization to an interaction is in progress. I will skip this slide about finite system because of the lack of the time, and also because it's complicated. I hope you can trust me. If not, you can look into the original papers shown here that the found solution in finite system allow you to distinguish, at least mathematically, the gaseous phase from the mixed phase. Yeah, and what is interesting that all found solutions, the surface tension coefficient vanishes in the analog of gaseous phase. And so the power law distribution of clusters, bags, or nuclei will exist in gaseous phase. But now I tried hard to find something general about the other definition of critical endpoint. For example, I consider it isothermal compressibility peak, but unfortunately, there is no general conclusion for a finite system with size below 1,000 particles, because everything depends on interplay of parameters and so on, and even solutions in the complex energy plane. So the whole point is that it might be that for finite volumes, the location of critical endpoint might depend on the definition which you use. Okay, and these are my conclusions. So with the development of statistical models of quark-gluon bags with surface tension is on the right track. In a few years, I hope we will make them very accurate to infinite system. And then induced surface tension and curvature tension concepts should be extended to finite volume. And then we will have a chance to build the statistical mechanics of phase transition in a finite system. And if our colleagues who are working in Dyson-Schwinger equation approach or FRG or other effective models will also solve this problem, it will be great. We can compare with them. And another maybe pessimistic conclusion is that to employ the realistic equation of states for a finite system, we have to modify our hydrokinetic approaches in order to extend them to use complex free energy values and not only the pressure, but surface tension, curvature tension, and so on. Thank you very much for your attention.
Okay. So